Hi, and welcome back. This is the first lecture of three for Chapter 4. Now, the purpose of Chapter 4 is to take what we learned in Chapter 3 and extend it to 2 and 3 dimensions. Now, if you remember Chapter 3, primarily what we did was to build a foundation of concepts. Concepts like position, displacement, both instantaneous and average velocity, and instantaneous and average acceleration. Now, we spent quite a bit of time looking at a specific situation being a constant acceleration. So when you have a constant acceleration, what you can do is to derive a series of kinematic equations or equations of motion. And these equations of motion allow you to predict the velocity and the position of an object at some future time, and potentially even the acceleration if your acceleration isn't constant. Well, we're going to do the same thing here with Chapter 4. Now, that said, one of the convenient things about 2 and 3 dimensional motion is that in truth, what you're doing is working one-dimensional problems that are coupled by time. So, for example, let's pretend that you have something that's moving, along the x and the y direction like this, we'll say. So maybe it's moving this way. Here's its location right here. Now, as it moves along x, but it also moves along y. And since x and y are independent directions, we can treat motion in x, motion in y, and also motion in z as though they're one-dimensional. Now, what's the same between them, though, is the fact that the passage of time in the x direction and the passage of time in the y direction and potentially the passage of time in the z direction, they're all the same. So you end up working with a series of what are called coupled equations. Now, these equations are coupled in time. And to be clear, this is really only true for classical mechanics and things that don't depend upon relativity. You do things like that, things break very quickly. But we're not doing that right now. So, that said, to illustrate this point, what I'd like to do is to work a problem. So, we have a car that travels at a constant velocity of 15 meters per second northeast at 25 degrees relative to east. Find the distance the car travels and its location after 1.5 hours. So, the first thing, just like in Chapter 3, that you want to do is to draw a picture. Why do we draw pictures? Well, pictures allow us to potentially extract more information than what we're explicitly given. For example, we're not told where the car starts from. What that means is that that's up to me to choose. And what I'm going to do is to have the car start at the origin. Now, if I do that, that means that my initial position in the x direction is going to be 0. And my initial position, in the y direction is going to be 0 as well. Now, we also know that it's traveling at a constant velocity, and that means that the acceleration that this car is going to experience is 0, but we're going to get to that here in a moment. So let's just label our graph here. Here's our initial position for our car. Our car is going to go like this, making car noises. Somewhere over here, let's say about here, 1.5 hours in the future, this car has a position and a distance from the origin. Now we're going to get into how to find that here in a moment. Now, the car has got a velocity. Its magnitude is 15 meters per second. And it sits, if you think of x as east, and you think of y as north, it sits 25 degrees above the x-axis. Now, that seems to be about all the information that we've been given. So let's go over here and write out our givens and what we're trying to find. What are we given? Well, the velocity of our car initially, and I'm going to put a knot there to show that it's initial, is 15 meters per second, and it makes an angle of 25 degrees above east, or the x-axis. We're going to need to break this velocity into pieces. There will be a x part and there will be a y part, but we'll find those here in a little bit. Now, likewise, we've been given a time. We know we're looking 1.5 hours into the future. Now, we need to convert this time from hours into seconds in order to be consistent, because we're working in the MKS system. That is, we deal with meters, kilograms, or seconds, unless explicitly told otherwise. Now, we also know, based off of how our picture was drawn, that our initial position in x and our initial position in y are 0. We also know, because of the fact that we're dealing with a constant velocity, that our acceleration is 0. Now, how do I know that? Well, if you think about what acceleration is, whether it is average or instantaneous, they both depend upon velocity changing with respect to time. And if something is constant, it's not changing, which means that this would be 0 and this would be 0 as well. So what that means is that any acceleration that this thing would experience in the x direction would be 0, and any acceleration that it would experience in the y direction would be 0 as well. Now, what are we trying to find? We would like to find the distance that the car travels and its location. The location would be x and y, its position in the x direction and in the y direction at some time in the future, 1.5 hours. The distance, I'm going to call d, and just put it off here to the side, because in reality, we're going to call it r. That's what it truly is. We'll get to that in here in a little bit. Now, so we have our givens. We have what we're trying to find. The next thing we need to do is to take our time and convert, and then break our initial velocity up into pieces. Now, so let's start with our time. I know that there are 60 seconds in 1 minute, just like I know that there are 60 minutes in 1 hour. So if you do your math here, 1 hour is the same thing as 3,600 seconds. So I can convert my 1.5 hours to seconds by noting the fact that there are 3,600, get rid of that 0. Went to write an S and my hand wrote a 0 for every 1 hour. Now, if you do the math, and I'm going to do the math here, I can find my calculators right here. Here's my calculator. It is 1.5 times 3,600. 5,400 seconds. Now, I'd like to point out here that this has 2 sig figs, this has 2 sig figs, and this has 2 sig figs as well. So at the end of the day, we're going to be rounding to 2 sig figs. Not yet, though. Remember, we want to keep any rounding done at the end. So we've converted our time. Now let's handle our velocity. Well, to do that, let me draw a small little coordinate system right here, just to sort of facilitate this. This would be our velocity vector that we need to take and to break up into components. And this is the y direction, this is the x direction. The length of our velocity vector, I'm going to call v naught. Now, this part right here of v naught would be v naught y. And this part right here of v naught would be v naught x. And if you take and you take your trig functions and you write them in terms of this, we know, given that that's theta, that sine of theta is opposite over hypotenuse. Now the opposite side is v naught y, and the hypotenuse is v naught. Cosine of theta, for example, is adjacent over hypotenuse. The adjacent side is v naught x, and the hypotenuse is v naught. Now, we're going to take these two and use them to find out v naught x and v naught y. V naught x, for example, is v naught times cosine of theta. We'll find out what that is here in a second. And v naught y is v naught times sine of theta. Now, let me scroll this down just a touch. So let's plug our numbers in here. V naught is 15 meters per second. This is going to be cosine of 25 degrees. This is 15 meters per second. And this is going to be sine of 20. Whoops, that looks more like a 3 than a 2, doesn't it? 25 degrees. So let's plug these into our calculator. So in x, we have 13.59 meters per second. Obviously, that's rounded. And in y, we have, oops, there we go, 6.34. Okay. Now, so let's put that up here where we made space for it under the givens. 13.59 meters per second, 6.34 meters per second there. So I think we have everything that we need now to actually get started. That said, what we want to do here is to, just like before in chapter 3, write down our equations, except we're going to have 3 in the x direction and 3 in the y direction. Now in the x direction, we would, from experience, have v is equal to v naught plus a times t. But to show that this belongs to the x direction, we need to take the things that are vectors and put x's on them. So there's an x, there's an x, and there's an x. It's the same equation. All we've done is to take and put x's here. For y, it's the same thing except you put y's. It looks like that. Now, so the next equation would look like x is equal to x naught plus 1/2 at squared plus v naught times t. But just like before, we want to show the things that lie in x that they lie in x. Same thing here for y. Now the third kinematic equation looks the same as it did before. Vx squared minus v naught x squared is equal to 2 times a sub x times x minus x naught. And over here, vy squared minus v naught y squared is equal to 2 times a sub y times y minus y naught. So the equations look the same. All I've done is to re-index them to show that they lie along x or along y. Now the next thing we're going to do is to take and plug in our givens. That is the zero ones, so we can simplify. We have initial positions that are zero, and we have accelerations that are zero. So what that means is that this is zero, 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 and zero. Now, these two equations at the end of the day tell us what we already know. Our velocity is constant. That is, at any given time in the future, if we were to ask the question, what's the velocity in the x direction? What's the velocity in the y direction? What's the velocity in general? Well, it's going to be 15 meters per second, and it's going to be at an angle of 25 degrees with respect to east. And that's because our velocity is constant. These reiterate that. It's these equations right here that are useful to us. So, x is equal to v naught x times t. Y is equal to v naught y times t. Now, let's plug in the information that we have here. Let me just scroll down here a touch. V naught x is 13.59 meters per second. And t up here is 5,400 seconds. Now, I want to stress that when I wrote this down, I rounded it. Were you to actually perform this calculation, you would want to use all of the digits that your calculator told you. Typically, you store this in the memory of your calculator and then multiply it by this when you're ready. I'm not doing that here because I rounded it when I wrote it down. So, when I take and I plug the stuff into this, we have 13.59 times 5,400 seconds, 73,386. So this would be 73,386 meters. Now this is obviously before I round anything. Now this one over here, let's plug in the y stuff. Y was 6.34 meters per second. Again, is traveling in that direction for 5,400 seconds. 6.34 times 5,400, 34,236. Okay, so the distance that we travel here is this right here, going up to our point here in space. Now, that can be found using the Pythagorean theorem because this right here would be the y part of that vector or that right triangle, and this right here between there and there would be the x part. So the distance, d, which is also the same thing we're going to discover here in a moment as r, is the square root of the distance traveled in the x direction squared plus the distance traveled in the y direction squared. So when you take and you plug your stuff in here, you get 73,386 meters squared plus 34,236 meters squared. Now, when you take and you put that in your calculator and you do it, 73,386 squared plus 34,236 squared. It's 80,979 meters. Now, so here's how you would want to write your final answer. You could say that my position in space, which is in the x position, the y position is equal to, rounding this to 2 sig figs, 73,000 meters in the x direction plus 34,000 meters in the y direction, or 73 kilometers x hat plus 34 kilometers y hat. It's entirely acceptable. Now, the distance traveled is the magnitude of r. 81 kilometers, or 81,000 meters. Either is fine. Now, you could also express, since we're trying to find not just the distance that the car travels, but its location, you could also express your location here as r vector is equal to 81 kilometers with an angle of 25 degrees above east. Why do I know that the angle is 25 degrees at the end of the day? Well, it's traveling at a constant velocity. The angle isn't going to change, but you can prove it to yourself by using the inverse tangent function. Now, here, the opposite side would be y, and the adjacent side would be x. (34) 236 meters divided by 73 386 meters, and if you do this, you get 25 degrees. So, at the end of the day, how do you write it? The distance traveled was 81 kilometers. Or, if you want, you can write it as 81,000 meters. That's fine too. The location of my car after 1.5 hours is 73 kilometers in the x direction plus 34 kilometers in the y direction, or, and this is entirely equivalent, r is 81 kilometers 25 degrees above east. These are fully equivalent. All right. Now, I prefer this because it makes you sort of go through the trig routine, and that's so you don't forget it. But either way works. Now, that said, let's talk more about the vector nature of these things. So if you remember earlier, I mentioned that, part of the purpose behind Chapter 4 is to take the concepts that we learned in Chapter 3 and extend them from 1 dimensions into 3 or into 2. Now I'm going to stick with 2 for the meantime, just because 3 is pretty easy. All you do is just add an extra thing to the end. You'll see that here in a moment. But that said, one of the first concepts we talked about, if not the first, was the concept of position. Now, I just introduced you guys to 2-dimensional position. So the position of something would be its location in space, obviously relative to the origin. So let's pretend that you're pointing over here at, I don't know, some objects. There's your object right there. This would be its position vector. Now, it has an x part and it has a y part as drawn. It could have a z part if we extended it out of the page. Now, so let's pretend that your object starts here and does something over here, and maybe it ends up over here. There's your new place. So this would be its initial position, and this would be its initial x position and its initial y position. Here it is, sometime later on, here like that. So here's this new position in space. I'll call it r. Has an x position, has a y position. Now to get from here to here, this right there is the path, or at least the straight line path. Now, if you remember, we had defined some time ago displacement as being where you end up minus where you started from. So the question is this displacement? Does it look like that? Now, so here, would be what your displacements look like just along the one-dimensional stuff. So the question is that if we perform this calculation, do we end up with components in x, y, and potentially z that look like this? Well, let's try it. So delta r, if we follow the suggested form, would be where you end up minus where you start from. Where do you end up? Well, it's going to be x in the x position plus y in the y position. Where did you start from? Your initial position in x, x hat, plus your initial position in y, y hat. Now I'm going to group the things that deal with just x hats together and just y hats together. X minus x naught, x hat, plus y minus y naught, y hat. And look at that. That is in fact delta x and in fact delta y. So what that means is that the concepts of displacement are the same in two-dimensional and three-dimensional vectors as they are in one. All you do is abandon x, y, and z as specific coordinates, call it r, and put a vector over the top. That's all you do. Now we're going to find out that this is true for the most part throughout the whole thing. For example, after we talked about position and displacement, the next thing we talked about was average velocity. At least the average stuff right here. We'll do instantaneous as well in a second. Now, so velocity here, average at least, we defined in the x direction to look something like this. In the y direction, it would look presumably something like this. And as you can imagine, in the z direction, it would look presumably something like this. Now, the bars here mean average. Now, when you take and you promote this sort of stuff to a vector that's 2 or 3 dimensions, you don't want to put the bar over the top. It gets confusing. So what you do is you just write AVG on the side and call it average. So the question is does the form hold true? Is this a true statement? Okay. Well, to see if it is, let's take a look. So basically what we're doing is we're taking and we're dividing delta r, which we calculated over here, by 1 over delta t. Well, as we saw with delta r, it was x minus x naught, x hat, plus y minus y naught, y hat, z minus z naught, z hat if you wanted to. And this is delta x, and this is delta y. So what that means is when you divide through, you have a delta x over delta t here, and you have a delta y over delta t here, which means that v average is in fact the average part in x plus the average part in y plus potentially the average part in z if we wanted. So it holds true. This is a true statement right here. So what we have is this. We have, given that our position looks like x, x hat, y, y hat, and maybe even z, z hat, I'll throw that in there, that our displacement is just r minus r naught. And that average velocity is how your displacement changes, or how your displacement over time, rather. So the forms are the same. They're the same. Now, so the question is what about instantaneous velocity? Well, instantaneous velocity, if you remember, looked something like this. It had derivatives in it. dx dt, dy dt for y, dz dt. So, this is your position. You're taking the derivative of your position as a function of time. So the question is it true to say that your velocity, your instantaneous velocity at least, would be what you get when you take the derivative of your position vector over time, or with respect to time? And the answer is yep, sure is. But we're going to see here. Let's just go ahead and carry it out. This would be d by dt of x hat plus y hat. You could put a z hat here if you want. I'm not. I'm just going to cut it short because it's just the same process. Now, x hat, y hat, and z hat potentially are unit vectors. They always point along x, y, or z. So the direction is constant. And they have a value of 1. Like their magnitude is 1. So they are, in truth, constant vectors. And by now, through calculus, you should know that if you take the derivative of a constant times a variable, you can pull the constant out. Basically, what you're doing is you're following through with the product rule, but on the term that you take the derivative of the constant with, that ends up being 0, and it doesn't contribute. So this would be the same thing as pulling the constant out and then taking the derivative of the thing that's left. You're pulling the constant out and taking the derivative of the thing that is left. And if you look here, this, in truth, is your instantaneous in x, and this is your instantaneous in y. So it's your instantaneous velocities. So this is a true statement. Okay, so this is in fact what your velocity looks like. Now you can prove to yourself, if you would like, that acceleration works the same way. It would be the derivative of your velocity vector with respect to time, or two derivatives of position with respect to time. This is true. Yep, this is how it works. Okay, now, not only that, check this out. Let's look at our kinematic equations. So these over here were them. They're all marked up on though. So why don't I just rewrite them? In x, I'm going to write the first two. I'm not going to write the last one. The last one is a consequence of doing a dot product, and we'll get to that later on. But in x, you have Vx is equal to V naught x plus Ax times t. You also have x is equal to x naught plus 1/2 Ax times t squared plus V naught x times t. In y, Vy is equal to V naught y plus Ay times t. And you have y is equal to y naught plus 1/2 Ay t squared plus V naught y times t. So these are two of the three kinematic equations written in x and y. What I would like to do is to take and note the fact that r looks like x hat plus y hat. Okay, now remember, x is your position along the x-axis, and y is your position along the y-axis, which means that I could take and I could plug in this for x and this for y right here. We're going to do exactly that. X naught plus 1/2 Ax times t squared plus V naught x times t. That's the x part. The y part looks like this. Y naught plus 1/2 Ay times t squared plus V naught y times t. This is in the y hat direction. Now what I want to do is to take the concept terms and group them together. This, for example, would be initial position. This is acceleration. And this is initial velocity. Now, that said, when you group them, you have x naught x hat plus y naught y hat. That's the initial position part, the first term. the second term, I'm pulling the half out of front of both the terms, leaving ax times x hat and ay times y hat in there, and pulling the time out of the right-hand side. If you multiply that through, you'll see you get exactly the same thing. That's the terms right here. Next up, that one right there. V naught x, x hat, plus V naught y, y hat, times t. Now look, this is initial position. This is acceleration. And this is initial velocity. And what that means is that we can write this the following way. Looks just like the old one. All we've done is switch out x for r and put vectors over the vector things. It works. Now, we can do the same thing to the top one, but using this suggested form, I could pretty much guarantee you it's going to look like this. And it does. So as you can see, our kinematic equations that we derive for places in which you have constant acceleration work exactly the same way in 2 and 3 dimensions. Now, that said, this form right here is convenient, but it's not the form that I want to use right now. I want to stick with just looking at what's going on in x and just looking at what's going on in y and coupling them through time, which is technically what we're doing here. It's just more compact. And I want to do that with this problem right here. Now, this is a projectile motion problem. You have a constant acceleration. It's due to gravity. And to solve this, we're going to have to work a reasonably long, but not too complicated problem that deals with projectiles. Okay, so in this one, we have a cannonball that's fired at 150 meters per second and with an angle of 65 degrees above the horizontal. We need to find the range of the cannonball, the max height it reaches above the ground, the total flight time, and its velocity upon impact. Now, the way I want to approach this problem is by breaking it up into 2 pieces. So to begin with, let me draw our picture that we always do here. I'll label some axes here. This is the y-axis. This is the x-axis. We're drawing an extra long x-axis so I can show you what range is. Here, we'll say is the velocity that the cannonball is being launched at. So your initial velocity would be 150 meters per second, making an angle of 65 degrees above the x-axis. So this is 65 degrees, and obviously the magnitude of V naught is 150 meters per second. Now, so if you think about the path that this thing would take, and I'm going to try to sort of freehand this, you launch it, it goes into the air, covering both x and y, hits a peak right there, and then comes back down to the ground like this. Hey, that's not bad. That's a pretty good parabola. I'm going to pat myself on the back for that one. Now, so this right here is what's meant by range. It's actually a ballistics term. It means the total distance along the ground that something travels. And in this case, the ground is the x-axis. So this right here, this distance right here, is the range. And conventionally, we actually use the letter R for range. Now, so we also know that the flight of this thing is going to be determined by the acceleration due to gravity. Let me fix that real quick. So this is approximately the peak right around there. Oh man, Just have an issue here. Here we go. We'll do it again. So this is the direction of the acceleration like that. Now, if you think about it, the way things are drawn with y being up and down, the acceleration here is 9.8 meters per second squared because it's free fall, but it's down the y direction. Now, this is the only acceleration because remember, free fall is only the acceleration due to gravity. Okay, so what that means is that there is no acceleration in the x direction, just in y. Now, this right here is approximately where the very peak of this thing would be. And at this point, we'd say that would be the max height. So I'm going to just draw it out here, actually. Obviously not at this point in space, but just because it's getting so busy near the peak there, approximately here would be the max height. Okay, so right here in space, translated over here, it's about there. Now, so that said, we do know some stuff about what's going on at this point. Like I said before, these are actually two one-dimensional problems. You have a one-dimensional problem in x, a one-dimensional problem in y, and they're linked by time. And we know that if you throw something up into the air, as it travels upwards like this, the acceleration due to gravity is robbing motion from it to the tune of 9.8 meters per second for every second that goes by. So, you throw it up into the air with a velocity initially of 9.8 meters per second. All it takes is 1 second for it to be slowed down all the way to rest. So at the max height, that's defined by your y velocity being equal to 0. Now, I want to be very clear, x is definitely not equal to 0, okay? And in fact, since there's no acceleration in the x direction, whatever the initial velocity in the x direction is, well, that's going to be the instantaneous velocity in x the whole way through. Now, when this hits the ground over here, it's going to, whoops, let me fix that again. It's going to leave a, I don't know what that's all about, but we'll go with it. It's going to be like that. There's your final velocity. Looks something like that. Now, I'm going to call this angle here alpha, and this final velocity is just v. So, if you remember back in chapter 3, the way I approached free fall problems was that typically you would break it up into two pieces, one piece where it's going up into the air and the other piece where it's falling back down. And that's exactly what we're going to do here. We're going to call this part 1. This is part 1 goes up to the top, and part 2 goes down to the bottom. Now, here's the thing. The goal here is to find everything we possibly can that we don't know already by solving part 1. Then we use the information that we get from that to plug in information that would be quote unquote given for part 2. Okay, so let me, down below here, we're going to draw two separate problems. There's going to be one like this. This will be part 1. And then one like this. This will be part 2. Like this. Okay. Now, there are a couple different ways we could approach this. I'm going to approach it like this. The first part, let me just go ahead and put y's and x's to be consistent here. So the first part has us launching up into the air with your initial velocity that we're given, like that. And it goes up into the air and then hits your peak right here. So at this point, we know Vy is equal to 0. We know once again, your acceleration due to gravity is down at 9.8 meters per second squared. Here's theta. Theta is 65 degrees. The magnitude of our vector is 150 meters per second. Now, so let's label a few things here again. This right here, this is going to be your max height, and this is also going to be your displacement in the y direction. Okay, so for the first part, that's your displacement in the y direction. This right here is part of the range in the x direction. So this right here, since it belongs to the first part, we're going to just index it as 1. Okay, so we have a max height. We have our part of our range. We also have at this point the first part of the time, t1 we'll say, because remember we need to find total flight time. So this is pretty much the entire picture for part 1. So for part 2, we start, we'll say here, and we fall down. Let me try to freehand this thing again, like this. Okay. So here would be our final velocity, whatever that is. So we need to find that. Here's our angle alpha. So this would be V. We don't know what that is. But look, so for the second part, our projectile starts from the position where the first part left off, which technically would be the max height. Okay. It's going down to the origin down there. Let me just be consistent, put the origin there as well. So, so we're going to take the max height we get from the first part and use that as the initial position in the y direction for the second part. Likewise, this right here would be the last part of the range. So call this x2. All right. And of course, by solving the problem, we'll find, the final time. And let's just go ahead and put our acceleration due to gravity in here. Once again, down like that. 9.8 meters per second squared down the y direction. Okay. So this looks pretty much it for part 1 and part 2. So like I said, I'm going to solve these things separately. So what I'm going to do here is to snag part 1. We'll just do like that. And let me copy that. And what I'm going to do is to come over here and paste it. Just drag it over here like that. Now, from here, what are we given? Well, we know an acceleration. Our acceleration in the x direction is 0. Okay, remember, we only have free fall going on here. So that means in the y direction, it's 9.8 meters per second squared down. Okay. We also know, based off of how we've drawn our problem, that our initial position in x and our initial position, in y is 0. So let's write that down. X naught is 0, y naught is 0. Okay. We're also given our initial velocity. Our initial velocity is 150 meters per second, making an angle of 65 degrees with respect to the x-axis. Now, we're going to need to break this up into pieces, just like we did with the velocity that we're given from the previous problem. Any other information that I have here? Well, I do know that my velocity in the y direction, that is our final velocity here, is 0. We don't know what the x is, but we're going to be able to find it once we break this thing up into pieces, because remember, there's no acceleration in the x direction. Now, what are we trying to find? I'm trying to find, let's see, everything else, basically. So we'll need to find final velocity in x for the first part. We'll do that, like I said, by breaking things up into pieces. We need to find the height above the ground that this thing goes, the max height. We need to find this first part's displacement. And we also need to find the amount of time it takes to get up to the top. Okay, all this is going to go into helping us backfill in, part two's givens, and also helping us answer the stuff at the end of the day. Now, so that said, let's go ahead and break our initial velocity up into pieces. We're going to draw a little coordinate system here. I should have lifted my hand before moving it on that. There we go. We'll draw it like this. Let's put our little vector here, like that. So this would be y, this would be x, this is theta, this is v naught in length. And so what that means is that this part of the v naught vector is going to be v naught y, and this part right here, the v naught vector, will be v naught x. So if you think of, and just for completion's sake here, I'll fill them in like that. There's v naught y, and then this would be, v naught x, like that. I think it's trying to force me to put it there, but it won't win. There we go. So there's v naught x like that. Okay, so anyway, as I was saying, if you write out your trig functions, so like we know sine of theta, for example, is opposite over hypotenuse. In this case, opposite is v naught y, and the hypotenuse is v naught. Cosine of theta is adjacent over hypotenuse, or hypotenuse right here. So the adjacent part is v naught x over v naught. So using these two, we can very easily find out v naught y and v naught x. V naught y, for example, is v naught times sine of theta, and v naught x is going to be v naught times cosine of theta. So let me plug the stuff in here. V naught we know is 150 meters per second. Sine of theta is 65 degrees. This is 150 meters per second. Cosine of 65 degrees. So let's go ahead and plug this stuff into our calculator and find out what we get. One second. 150 times sine of 65. That's going to be 135.94 over 95. 135.95 meters per second. That's pretty tight there. Okay, and let's do the same thing for this 150 times cosine of 65. 63.39. So 63 point, whoops, 39 meters per second. Woo! Boy, that's really close, huh? All right. We'll put a very tiny seconds under there. There we go. So, 1 second here. So now, and before I just plug in what Vx is equal to, because we can find it, it's going to be this right here. Let me just sort of illustrate the point. So if you remember, what we've done in the past is after we've written down our givens, and after we have put in what we're trying to find, and we've done everything we need to do here, the next thing we do is we write our equations down. So let's go ahead and do that in x and in y. Okay. So in x, remember, all you do is you write your equations and you just put indexes on them, or indices on them. So this would be Vx is equal to V naught x plus Ax times t. This would be Vy is equal to V naught y plus Ay times t. This would be x is equal to x naught plus 1/2 ax times t squared plus v naught x times t. This is y is equal to y naught plus 1/2 ay times t squared plus v naught y times t. This is vx squared minus v naught x squared is equal to 2 times ax times x minus x naught. And this is vy squared minus v naught y squared. And that's equal to 2 times ay y minus y naught. Now, check this out. So we know our acceleration in the x direction is 0. Why do we know that? Well, the only thing that we're dealing with here that's causing a change in motion is gravity. And gravity always pulls you towards the ground. And in this case, the ground direction is y. So, given that, ax is 0. That's 0, that's 0, and that's 0 as well. Now, before I plug in any other stuff that I know, I want to point out that what this says is that our velocity in the x direction at any given in time is the same as the initial velocity in the x direction. So what that means is that here, I don't know why that got there. Here, this is 63.39 meters per second. It's going to be true for the first part of the problem and also true for the second part of the problem. Now, what that means is we actually know part of the final stuff. We wanted to find the velocity of this thing upon impact. We already know the x part of the final velocity. We need to find the y part. And that's because there's no acceleration in the x direction. Now that said, let's go ahead and plug in our stuff here. X naught and y naught are 0. X naught's 0. Y naught's 0. Y naught's 0. Vy at the top is equal to 0, so that goes away. That goes away. And that looks to be about it. So really, this equation right here is the only useful one for the x stuff. So we have x is equal to v naught x times t from this side. And from this side over here, we have that v naught y plus ay times t is equal to 0. We have y is equal to 1/2 ay times t squared plus v naught y times t. And we also have minus v naught y squared is equal to 2 ay times y. Okay? Now, so we have this list of stuff that we're trying to find, but we've already found this one. And that's because there's no acceleration in the x direction. We know vx is going to be vx is going to be the vx the whole time. So we have some options here. What I propose we do, just from a simplicity standpoint, is to find time to begin with. So time is going to come from this equation right here. And if you solve it for t, t is equal to v naught y, the minus sign out in front, over ay. So if you plug that in, v naught y is up here, 135.95 meters per second. Okay. The acceleration we know, that's 9.8 meters per second squared down. Now the negatives cancel, which is a good thing. Well, like I said, we always want positive times. That's the only thing that makes physical sense here. And so 135.95 divided by 9.8. 13.87 seconds. So there you go. For the first part of the problem, that's the time, T1. So what I'm going to do is to go up here and to record that. T1 is 13.87 seconds, and then take it off the list. Now, next up, we could find displacement in the x direction. Here, remember, displacement is x minus x naught, but x naught is equal to 0, so really it's just x. So we'll use this for displacement, and v naught x, as we found out before, is 63.39 meters per second. And at the end of the first part, well, that happens 13.87 seconds into the future. And if you do your math here, it ends up being about 63.39 divided, or not divided, times 13.87, 879.22, something like that. Okay. So again, record it. All right. So that takes this off the list. Last up is the max height, or delta y. We've got options. We could use this, but doing this is more complicated than using this. And this is what I propose that we do, is we use this one right here. So max height is going to come from this equation right here. Minus v naught y squared is equal to 2 ay times y. If you solve for y, it's minus v naught y squared over 2 ay. V naught y squared is 135.95 meters per second. You got to square that. Don't forget to square it. Again, common mistakes are not squaring things. The square here on the time, the square here on the velocity. AY again is 9.8 meters per second squared down. The positives or the negative signs cancel, giving us a positive y, which makes complete sense based off of our picture here. So if I do this, 135.95 squared divided by 2 times 9.8, 942.98 meters. So there you go. What is our displacement in the y direction? 942.8 meters. Okay, so here's what we have. That's all the information that we obtained from the information that we were given in the first part in solving stuff. So what we're going to do now is to take the second part and solve it. So let me snag it. Copy it. I need to add another page. I'll do it here. Let's paste. Move it up over here where we can actually work on it. And get to work. Now I am also going to sort of snag this right here because I'd like to use the information from it to fill in stuff. And so let me copy that. I'm going to put it over here and just sort of put it off to the side. Maybe off here like that, just a reminder. So this is from part 1. So now let's fill in our givens and what we're trying to find here. So again, we know in the x direction, no acceleration. In the y direction, it's free fall acceleration. It's due to gravity. Now, we're going to call here, again, our initial position in x 0. But look where our initial position in y is. Now it's way, way up above the ground. But we get that information from what we got from part 1. This right here is where we're starting from now, 942.8 meters. Okay. Now, we also know from here that at the very top, our velocity in the y direction is equal to 0. And on this part, we're starting from the top right there, which means that our initial velocity in the y direction is equal to 0. But our initial velocity in the x direction is the same thing it's always going to be because of no acceleration there. And we got that, from doing our solution to the first part, noting the fact that there was no acceleration. Now, this looks to be about it, okay? So given all the stuff that we have here and what's left, what's there left to find? Well, delta x2, again, I'm subscripting it by 2 to show that it belongs to part 2. We need to find this displacement because given the displacement from part 1 and the displacement from part 2, you add those together and you get the range. We need to find the time for part 2, and we need to find the velocity that it has upon impact. We already know the x component. That doesn't change. So technically, what we really need to do is to find Vy. Okay, so the next step we know is to write down our equations in the x direction and in the y direction and plug stuff in and see what simplifies. Oh yeah, that reminds me. Guess what? When you hit the ground, what's your final position? 0. So technically, we start off here with our initial position of this, and our final position, y is equal to 0. Let's not forget that. Okay, so let's write our equations down. I have Vx is equal to V naught x plus Ax times t. I have x is equal to 1/2 Ax t squared plus V naught x times t. I have Vx squared minus V naught x squared is equal to 2Ax times x minus x naught. Now in y, I have Vy is equal to V naught y plus Ay times t. I have y is equal to y naught plus 1/2 Ay times t squared plus V naught y times t. And I also have Vy squared minus V naught y squared is equal to 2 times Ay times y minus y naught. Okay. Now, so let's plug in the stuff that we know here that's 0. For example, I see Ax is equal to 0. We know that for a fact. I'm going to use a new trick here. Ax is 0, which means that this doesn't contribute. That goes away. Ax is 0. That goes away too. Ax is 0. That makes that equal to 0 as well. So again, from the x side of things, really the only equation that's useful to us is this right here. Okay. Now from the y side of things, I see that V naught y is equal to 0. And I also see that my final y is 0 as well. So V naught y is 0. Final y is 0. V naught y is 0. I'm going to try this. Final y is 0. V naught y is 0. So these equations right here give us Vy is equal to Ay times t, y naught plus 1/2 Ay times t squared is equal to 0, and Vy squared is equal to 2Ay times minus y naught. So we're trying to find the displacement in the x direction, the time it takes for it to fall, and the final velocity. But thankfully, we already have part of the final velocity. We got that. It's the x part right here. Remember, that doesn't change. So we just really need to find Vy. So I would start with time. This is where I would start, would be this equation right here. So here's our equation. There's y naught plus 1/2 ay times t squared is equal to 0. If I solve for t here, t is the square root of minus y naught times 2. So we'll say 2. I don't like how that looks. Let's just make this a little bit easier. 2 times minus y naught divided by ay. So if I solve this, 2 times minus y naught, let's see, y naught was 942.8 meters. The acceleration due to gravity is 9.8 meters per second squared down. You plug that in there, noting the fact that the negatives cancel each other off, giving us a positive under the square root, which is always a good thing, unless you're doing something strange. Let's see, 942.8 divided by 9.8, 13.87, huh? You know, that really looks familiar. What is this? You're telling me it takes the same amount of time to fall as it took for it to go up. You know, I've seen that before. I saw that in symmetric problems. And guess what this is? This is a symmetric problem. That's what it is. I'm going to make some predictions now. And the predictions are the following. My displacement in the x direction is going to be the same as this. And the y direction velocity, the y part, is going to be the same as, must not be here. It's going to be the same as this, except negative because it's going down. But let's see if that's true. Let's see if that bears out. Okay. So we found T2. Just recorded it. Next thing up, let's go ahead and find delta x2. Delta x2 is equal to x is equal to v naught x times t. And what's v naught x? Well, 63.39 meters per second. What's t? 13.87 seconds. And let's see here. 63.39 times 13.87. 879.22. Look at that. Look at that. Let's just go ahead and find Vy. Why don't we use this right here to find Vy? We haven't used this equation really to find velocity. So Vy in this case would be Ay times t, which would be 9.8 meters per second squared down times 13.87 seconds. So 9.8 times 13.87 and down minus 135.93. Minus 135.93 meters per second. Boring rounding, same number. Also, you'll notice it's negative, like I said. So here's what we have. We have solved this problem in entirety. We just need to put stuff together. So part one, or part A rather, was to find the range of the cannonball. Now the range of the cannonball is how far it went in x for part one and how far it goes in x for part two. You add those together. So here for part A, the range is delta x1 plus delta x2. Or since this is a symmetric problem, you just double the distance it went in x in the first part, which would be 879.22 times 2. 1,758 meters. We're going to round this in a second, not quite yet. Let's just put the numbers in. So for this one right here, for part B, where we're trying to find the max height it reaches above the ground, that was actually given to us from information from the first part. It was this right here. So the max height above the ground would be the same thing as delta y from the first part. That's going to be 942.8 meters. And again, we're going to round that in a moment. So for the third part, we're trying to find the total flight time. The total flight time is going to be the time it takes to get up plus the time it takes for it to get down. I'll call it T sub t. T1 plus T2, or since T1 and T2 are the same, as you can see here and you can see here, all you need to do is to take 13.87 and double it. 27.74. And again, as I said, we're going to round this stuff at the end. The last thing was the velocity upon impact. Now, to do that, we actually need to find alpha and find v. I already know that v is going to be 150 meters per second, but let's just sort of illustrate that point by doing this. So here's the angle that this thing will say is going to make into the ground. This right here would be the x direction. This right here would be the y direction. Here's alpha. So we know the x part here. We got that from noting the fact that the acceleration in the x direction is 0. So the initial velocity is the same thing as the final velocity. So that would be 63.39 meters per second. We also, for the y part here, just sort of proved a point that it's minus 135.93 meters per second. We're used to put meters per second up here too to be consistent. So here, v is going to be the square root of vx squared plus vy squared. And if you plug that into your calculator, you'll get 150. Okay. Alpha is the arctangent of opposite over adjacent. The opposite side is minus 135.93 meters per second. The adjacent side is 63.39. So if you plug that in to your calculator, you get 65 degrees. okay? But it's negative because of the negative sign here, so it's below the x-axis. So what is our final velocity here? It is 150 meters per second with an angle of 65 degrees below x, or negative 65 degrees works. Now, going over here again, note that this is 2 sig figs, this is 2 sig figs. So at the end of the day, when you round our answers here, this ends up being 1,800 meters is your displacement in x. This ends up being 940 meters is your max height, and it's in the air for about 28 seconds. Okay, so and there you go. So this is how you would approach a ballistics problem. And again, what makes our life easy here is at the end of the day, had we known that this was a symmetric problem, we could have circumvented a lot of the work that we had to do for the second part just by noting the fact that the time is doubled, the range is doubled, the velocity upon impact is the same as when it left. It's just the direction is below the x-axis as opposed to up. So we're going to take advantage of that later on. But I do want to point out that if the problem is not symmetric, like for example, let's pretend that you're firing something off of a cliff. So the starting point and the ending point in the y direction are not the same. It starts high and ends up low or something like that. And we're going to do an example of that later on. You have to work the full problem in entirety when you do that. So this concludes our first lecture on Chapter 4. Next lecture, we are going to do a whole bunch of problems. And I will see you then.